Welcome to The Explainer. Today, we're diving into a genuinely paradigm-shifting leap in technology. We're talking about taking actual, living biological matter and fusing it directly with electronic silicon hardware. It's a massive shift that is slated to completely redefine the very limits of processing power by 2026. Let's get right into it.
Okay, think about this for a second. What actually happens when your computer chip physically grows a brain? I know, it sounds like straight-up sci-fi, doesn't it? But we're looking at a rapidly approaching reality. We are officially entering the era of living computers, and it is going to completely upend everything we know about how technology works.
So what exactly are we dealing with here? Biosynthetic computing is a technology where we literally integrate living neurons, or synthetic biological tissues, straight into traditional computer chips. The industry calls these organic silicon hybrid AI accelerators. It's a huge departure from the purely electronic setups we've been using for decades. Instead of just forcing electricity through cold metal, we're moving towards systems that actually mimic the physical structure and that incredible natural efficiency of the human brain.
Section 1. The Living Computer Era.
The contrast here is literally night and day. Think about your traditional GPUs. It's this hot, rigid world of high-voltage silicon that, let's be honest, sometimes doubles as a space heater. They use fixed circuits and kick out so much extreme heat that you need massive cooling systems just to keep them from melting down. But then, you look at hybrid bioaccelerators. We enter this cool, highly adaptable world of biological cells. We get neuroplasticity, natural cellular efficiency, and they run at incredibly low heat because biological components just don't generate that intense thermal output.
Section 2. How wetware actually works.
Now, what's really fascinating is the mechanics behind this. It's an incredibly elegant four-step journey for a single piece of data. First up, signal conversion. A data pulse starts as a standard electronic signal from the silicon, but specialized sensors actually convert it into chemical or electrical pulses that living cells can read. Then, step 2, synaptic integration. That converted signal is fed directly into the wetware. These are living cells kept alive in a nutrient-rich environment right on the microchip. Step 3 is where the absolute magic happens, neural plasticity. Unlike a rigid silicon circuit, the biological parts physically grow and change their connections. The hardware literally rewires itself while it learns. And finally, step 4, data feedback. The silicon monitors how those biological cells react and translates that physical cellular response back to digital data.
Pulling off those 4 steps requires a totally mind-blowing mix of cross-disciplinary engineering. You've got synthetic biology creating super durable cells that can actually survive outside a host. Then there's microfluidics, tiny little channels engineered to constantly deliver oxygen and nutrients to keep those components alive. On the silicon side, neuromorphic engineering designs the chip itself to mimic the architecture of a nervous system. And you can't forget interface layers. You absolutely have to use protective anti-corrosion coatings because, well, slopping a wet, biological, saltwater environment straight onto metal computer parts is pretty much a recipe for an instant short circuit.
Section 3. Solving AI's energy crisis.
1,000 times. Let that sink in for a second. This isn't just some minor optimization. It's a total revolution. The source data shows that biosynthetic chips use up to 1,000 times less energy than traditional chips to do the exact same tasks.
This sheer level of efficiency completely slashes the current AI bottlenecks. First off, that massive energy reduction drastically cuts operational costs. Data centers won't need to spend nearly as much on power and massive cooling systems. Second, it unlocks true parallel processing capabilities, letting computers calculate millions of things simultaneously, exactly how biological brains do. Third, the operating temperatures drop way down. And fourth, you get enhanced learning. Because the chip operates like a brain, it learns incredibly well from super small datasets. You just don't need those massive, power-hungry datasets that traditional models rely on anymore.
Section 4. Real-world practical impacts. Let's move this out of the server room for a minute. What does this actually mean for you? Abstract science is amazing, but this tech is about to fundamentally change the devices you use every single day.
So here's how it impacts your daily life. First, local mobile AI. Thanks to extreme miniaturization, AI capabilities that used to take up a whole warehouse of servers will soon fit right in the palm of your hand. Your phone will run heavy AI locally with no internet and without instantly killing your battery. Second, real-time health monitoring. Wearables are going to use biological sensors to track your health data in real time with hyper-precise accuracy.
Third, a massively decreased carbon footprint since the global tech industry can finally run energy-efficient data centers. And fourth, robotics. Robots running these hybrid chips are going to react to their environments with a fluid, lifelike intelligence that we just haven't seen before.
But to actually build this future, the industry needs a totally new kind of workforce. We're seeing a massive surge in demand for brand new career fields, specifically bioengineers and hybrid system architects. We literally need professionals who are fully fluent in both biological science and computer coding to design and maintain these systems.
Section 5. Risks and ethical limits. So, the crucial point we really need to understand here is that living hardware comes with some very unique physical vulnerabilities. Number one, biological components have a limited lifespan. They can literally die, which means parts of your chip will eventually need to be regenerated. Second, they are extremely sensitive to temperature and physical shocks. Drop your laptop, and you might actually give it a concussion. And third, the risk of biological contamination. If those microfluidic channels leak, you're not just dealing with a busted wire, you're leaking nutrients and living material right onto the rest of your computer hardware.
And beyond the physical risks, there are some pretty massive manufacturing dilemmas. Companies have to figure out if they're going to use lab-grown human neurons, animal neurons, or stick to fully synthetic protein-based circuits. It's a huge material choice, which is exactly why industry leaders are frantically trying to establish standardization protocols and setting up super strict ethical reviews for sourcing these materials.
Which actually brings us to a really profound quote from the source material. It reads, "Using living neurons raises questions about the definition of life and the rights associated with biological computing matter." Think about that. We are using learning, living matter as industrial hardware. It presents a deep, complex philosophical dilemma that the tech industry has literally never had to navigate before.
So, I want to leave you with this final, vital question. Where do we actually draw the line between a machine and a living organism? As this shift to biosynthetic computing really takes hold in 2026 and beyond, that line is going to get incredibly blurry. It's a fascinating, awe-inspiring, and maybe a slightly daunting future. I really hope this explainer helped clarify the incredible science and the weighty implications behind it all. Keep questioning the future, keep learning, and we'll catch you in the next one.